the dire situation. The town of Gainesville, Maryland is subject to the following hazards: flooding, erosion, environmental impacts, and cases of poor water quality. A couple of examples are shown on the right here, where we see falling trees due to erosion and a situation in which runoff goes directly into the shore. Additionally, these hazards are fueled or intensified by global and local conditions such as climate change and rising sea levels, Gainesville's low topographical elevation, poor stormwater management throughout the town, and also a loss of vegetation. Now we'll be looking into the current situation through two lenses as they apply to our team's goals and the response we came up with for the Gainesville community. The picture on the right shows a buoy associated with the National Oceanic and Atmospheric Administration, NOAA. These systems can collect wave data, but can be very costly. In terms of wave data collection in Gainesville, there isn't a buoy located directly in the vicinity of this town. One located near it is associated with the town of Annapolis, which is about 14 miles or 22.5 kilometers away from Gainesville, as we see in the map on the left. For the current situation in terms of water quality data collection, one of the sources of testing is conducted by the Cardinal Rivers Federation, and they perform field testing throughout the various sites shown in the map on the right, twice a month from April to October.
Our focus was to look into the flooding issues in Gainesville, Maryland. So we looked at the priority stream restoration map and decided to focus on Zone WR5. We looked at a topography map and determined that the majority of the excess water comes from the stormwater that runs down from the hills and into the streams. So our goal was to offer strategies to manage and mitigate damages from these flash floods, and the design that we came up with was a water wheel.
Once we decided for part of our design solution to include a water wheel to decrease velocity of incoming water, we used Autodesk Fusion to create a simple 8-spoke wheel with a basic stand to hold the wheel, while also allowing it to spin. The dimensions were also scaled down to fit within the vertical water tank that was being used for testing. And since this was being used to test its potential to decrease the velocity of running water, later versions of this design is open to different scaling options and various changes to improve its effectiveness.
For our experimentation, we placed our water wheel design into a small side-view flow visualization tank. This tank was set up in a manner so that we could record our experiments and analyze it through MATLAB. Originally, because of the fixed nature of the wheel, we tried to use the tank with a provided blocker as originally intended, but found that the water pressure of the tank was very low and not focused enough on the wheel to provide any noticeable change in velocity or movement. Instead, we decided to place a small hose in the tank held by the blocker to increase water velocity and direct the water at the wheel. This setup provided a more focused flow of water and allowed the wheel to spin freely.
Once we had a recorded video of water passing through the water wheel, we imported it into PivLab to analyze the velocity of the water before and after passing through it. First, the extracted frames had to be pre-processed by adding a mask over the background, so the main focus was on the velocity vectors of the water going through the wheel. Then after being analyzed, the velocity data had to be calibrated to convert the units from pixels per second to meters per second, and the plot adjusted to make the resulting data more easily understood via temporal mapping, where higher velocity water is indicated by a yellow color and lower velocity water indicated by a blue color.
After conducting our tests and analyzing the footage, we found a significant drop in velocity by about half, effectively proving our initial concept was a success. Upon finishing our initial tests, however, we discussed how we could improve our water wheel design and concluded that lengthening, angling, and adding a slight scoop to the end of the fins could be more beneficial and would help show better results in the flow visualization tank.
Thanks to the testing that we were able to do with the water wheel prototype, we can see that it will slow down the velocity of the water, and this can have different applications with water retention ponds or just slowing down the water in general to have more control over the flow and decrease the kinetic energy of the stream. But there is also potential in converting the rotational energy of the water wheel into stored energy for power that could be used for any type of water sensors that we might implement, or depending on how much energy is actually generated, we could offer it back up to the community. So this could be an interesting place to go from here, as well as testing the water wheel in conjunction with other designs and structures, such as the water retention pond.
Our team looked at two components for our proposed design. First, the upper watershed of WR5 through WR7 retention systems, and next, the shoreline/marine breakwater boardwalk and softscape preservation. For our approach of the upper watershed, we emphasized the use of offline retention systems, supplemented by small inline step retention features when necessary to slow stormwater velocity and reduce sediment transport. To further improve performance, each offline system would be equipped with a forebay located at the inlet. The forebay will act as a settling basin, capturing coarse sediments and debris before the water enters the main storage area. This design improves water quality, reduces sediment buildup in the primary pond or cisterns, and lowers the long-term maintenance requirements. For our upper watershed design, we wanted to test the diversion dam by mocking up a small-scale dam that would allow slower stream flow rates through while diverting the stream at higher velocity flow rates. The sand table experiment proved to be less informative than initially hoped for a few reasons. Our design for the representing a culvert was not restrictive enough to divert water to the retention pond during flooding events. The material representing soil in the sand table was more buoyant than we had expected, which led to challenges with predicting how the sand would react to our test. There was much more groundwater flow rate than we expected as well. For the shoreline design, we developed two primary concepts: boardwalk breakwater system and softscape preservation for marshlands and natural shoreline. The boardwalk breakwater system combines storm surge protection with expanded community space. Constructed as a raised offshore breakwater, the system reduces wave energy and protects against coastal flooding, while serving as a foundation for public boardwalk. This boardwalk would create new opportunities for walking, biking, and gathering along the shoreline. It could also incorporate small docks for kayaking, swimming, and boating to ensure the waterfront activities remain central to the community life. To strengthen cultural connections, the boardwalk could feature interpretive signage and historical stops highlighting Galesville maritime heritage, such as traditions of oyster harvesting, sailing, regattas, and boat building. For the breakwater testing, we utilized PIV Labs' velocimetry analysis program. Through our investigation, we determined that the most effective solutions for the Galesville watershed and shoreline must balance three primary community needs: flood control, ecological considerations, and enhanced public space. Our design approach integrates these priorities into the system that manages stormwater while improving resilience and the quality of life in the Galesville community. The upper watershed, consisting of WR5, WR6, and WR7 retention systems, and the shoreline protection with the breakwater boardwalk and softscape prevention. Together, these measures create a sustainable, multi-benefit system that reduces risk from flooding and erosion, supports ecological health, and expands recreational access. By aligning engineering solutions with community values, this project provides Galesville with a path forward toward a long-term resilience and shared benefit.
This slide shows the evolution of our buoy design. We started with a simple base shape which guided the final structure. Our first iteration included side handles for easier carrying and introduced the dual mounting system, visible in the section view. However, we later redesigned the upper section to better fit the battery and removed the handles since they were structurally weak in PLA. The final vessel was printed and coated with Flex Seal epoxy for added durability and waterproofing. Here's a close-up section of the lower portion. This area includes the dual mounting system. The Apple Watch sits in the outside, ideally in the water, while the wireless charging dock is positioned inside. The wall at the interface is deliberately thin, allowing inductive charging to pass through while keeping the charging components sealed and protected. Now we move to the upper portion of the buoy. which houses the battery. At the top, a clear acrylic panel allows sunlight to reach the solar power bank. This setup ensures continuous charging of the system and keeps the electronics safely enclosed. Finally, here's the internal layout. On the left, the charging dock is secured in place using a slide lock with dovetail joints. On the right, we added a bag of steel beads taped above the dock. This added weight lowers the center of mass, giving the buoy self-righting stability, even in waves. Here is the fully assembled buoy with the acrylic panel mounted on top and the battery secured inside its compartment. On the right, you can see the exploded SOLIDWORKS model, which highlights how each part fits together in the final assembly. For water quality applications, our buoy can be redesigned or retrofitted to hold in-situ sensors. The table here lists several recommended sensors from our research that could be integrated into the system for expanded monitoring. This map shows the intended deployment site. The buoy would be placed a few kilometers offshore, close enough for easy retrieval while still collecting meaningful coastal data. These sensors could be deployed in smaller waterways or coastal areas where current monitoring and networks have data gaps. While the sensors themselves can be costly, our buoy remains far less expensive than professional grade systems, which often cost tens of thousands of dollars. Additionally, it provides high frequency sampling, which improves overall data quality. In this particular slide, we show a area of the Galesville watershed where there are untested areas near trash sites, the trash sites being the yellow pluses on the map.
Hello, I'm Elizabeth and I will be talking about floating flotation ring. On our buoy, we grow ova, which can be called seed lettuce, and gracilaria. Ova grows fast, can live in many conditions, and the buoy gives it place to attach. It provides food for small fishes and help clean the water. Gracilaria grows well in shallow water, tied under the buoy. It creates space for fish and small animals to live and breed. We choose these plants because they make the buoy not only an energy device but also a small habitat that supports marine life and improves water quality. We have recycled plastic bottles used for floating support and as part of the frame. Stainless steel wire provides shape flexibility and resists corrosion. Clothing fabric, a simple cover material, and also help for the plants. Here is our website called Ocean IQ. You can scan this QR code. It will be on our buoy and it can connect directly to our website. The website main page will show daily ocean activities and condition, a short introduction, link to our data page, and real-time updates, and also learning research about local fish, marine life, and flooding. And we have a section for Q&A.
And now the time has come for testing, a glance into our investigative journey. These are the two different locations in which we tested our sensor buoy prototypes. The first was the Fluids Lab in the University of Washington, Tacoma, and the second was the Thea Foss Waterway, also in Tacoma. It was actually a few minutes away from our campus. Now for our test setup, these were the first two trials and the various components we used, such as the electronics or plates that we used inside the buoy. And this was the third trial in the Thea Foss Waterway.
Here we show the final tests of our prototype. In trial 4, the buoy was deployed with a battery installed, but the added weight raised the center of mass, causing it to capsize. In trial 5, we adjusted the design by adding ballast weight, which lowered the center of mass and successfully stabilized the buoy. Here are the tables regarding the results of our tests. As you can see, most things did eventually function properly, but issues with the charging interface persisted depending on the watch used. The Series 10 Apple Watch seemed to have worked consistently while the Series 5 did not. And as previously stated, we did have to apply Flex Seal to the main vessel as the 3D printed components were too porous and weight had to be added to the bottom to counter the increase in the height of the center of the mass due to the battery being placed in the upper portion. When tested with the filtration ring, the buoy functioned properly. The only issue was that the ends of the wire that were cut were quite sharp, so we applied hot glue to the ends as a remedy, but not a complete solution.
Now, for a glimpse into our experimental results, we will show data obtained from the gyroscopic sensor of the Series 5 Apple Watch in Trial 5. This data, along with other kinds, were collected for this trial through the Sensor Logger app we installed on the watch, and was transferred to the iPhone paired to it through a CVS file from the app. Here we see scatter plots for gyroscopic data in the X, Y, and Z directions corresponding to a half second of motion. We also see the 3D version of this data below the scatter plots, and this was plotted with XYZ mesh by providing the data points to this software. Finally, the GIF next to the 3D plot displays the physical motion that generated this data.
Now we move on to potential future upgrades and recommendations. For future improvements, we recommend switching from PLA to ASA filament, which is much more resilient to sun and water exposure. Adding sealant to all joints, a strobe light for night visibility, and a dedicated solar panel mounted separately would also improve performance and durability, while relocating the heavy power bank lower in the design. Finally, while our current design is optimized for an Apple Watch, other smartwatches could also be integrated. However, compatibility depends on the sensors and apps available for each device, so careful consideration would be required when adapting the system.
In the future, we can put in these two plants, which called horsetail and Intromorpha. Next, we are thinking put in active carbon to absorb pollution in the future, and it may likely be the base of our floating ring. Moving mechanism for the buoy. Our buoy floats on the water and uses tidal currents for stability and extra power. Key components including small propeller fins to face the current, a solid power bank, and the thruster. This design lets the buoy either hold position or move when it needed.